Good morning, everybody. We're going to pick up in our notes today, our momentum and impulse notes, right under the example that we did for the impulse momentum theorem. So if we look at this paragraph, we're still looking at the baseball and the bat right up here in this paragraph. So we want to understand that if the bat gives an impulse of force acting in a time period to the ball to change the ball's momentum. But according to Newton's third law, if you remember, that's the law that says for every action there must be an equal and oppositely directed reaction, then that means the ball must give an equal and oppositely directed impulse back on the ball, because impulse is a force exerted in the same time period. So the bat's momentum also changes, and by the same amount. The two forces are the same, but oppositely directed. Both the bat's momentum and the ball's momentum will change, and by the same amount, because it's the same impulse. So they have the same change in momentum. So here it is. The bat applies an impulse to the ball. So if we take that to be the negative direction, because from the bat towards the pitcher was the negative direction, then the ball's momentum changes by a value of negative 36.5 Newton seconds. But likewise, the ball applies an equal and oppositely directed impulse on the bat. So the bat's momentum also changes, but by the positive value. Okay, now does this mean that the bat will be traveling backward at the same speed as the ball? No, because they have different masses, so their speeds must be different to get the same change in momentum. In other words, their changes in momentum are the same because the impulse is the same for both. But where the ball has a small mass, it will have to have a large change in velocity to have the same change in momentum as the big mass of the bat undergoes a small change in velocity. So the two changes in momenta are the same, but the changes in speed are very different because of the difference in the masses. Okay? Now, in this example, we defined our system to contain the bat and the ball only, nothing else. This is what we call an isolated system. An isolated system is those containing only the objects with which we are concerned, with no outside forces acting on either one. So in this case, there may technically be some air resistance, but we will ignore that. There might be a little energy lost to sound and deformation when the bat and the ball collide, but for the moment we're going to consider that an ideal situation and consider it to be negligible. So we know that the sum of the forces acting on the system, okay, is 0. The only forces we have within the system would be the force of the ball acting on the bat and the force of the bat acting on the ball. But since they're equal and opposite, they balance out anyway. So the net force is 0. This system is isolated. Now, that means we can look at the momentum of the entire system as long as it's isolated. The momentum of the entire system must always remain constant. This is what we call the law of conservation of momentum. Basically, it's telling us that the sum of the initial momentum of the system before they collided must equal the sum of the final momentum after they collide. Okay, because they have the same impulse, they have the same change in momentum, so we're not really losing momentum outside the system. What we're doing is transferring it from one object to another. Okay, One good way of observing conservation of momentum is to study what happens with the ball and the bat. They collided. So we're going to look at collisions briefly. There are two basic types of collisions. The first type is the elastic collisions. Now, in reality, elastic collisions truly only happen between atomic and subatomic particles. But a lot of times we will look at macro world collisions, certain macro world collisions as also being elastic. For example, a collision between two billiard balls on a billiard table. We a lot of times look at that as being elastic. Or maybe the collision between two hockey pucks on an air hockey table. We would also look at that, even though technically there's going to be some energy loss to sound, maybe some deformation during collision, maybe some heat to friction, but we're going to consider those to be negligible in cases like that. Now, in elastic collisions, two things are true. First off, the total momentum of the system is conserved, always. Whenever you have a collision of any kind, momentum must be conserved. However, in an elastic collision, kinetic energy of the system is also conserved. That means the total kinetic energy before collision of all the objects in the system added together must equal the total after collision. No kinetic energy is lost to sound, heat from friction, or deformation of the objects when they collide. The other type of collision is the inelastic collision. In the inelastic collision, all other collisions would be considered inelastic. You're going to be losing kinetic energy. So that is the major difference between elastic and inelastic. How are they alike? Both types of collisions conserve momentum. So it doesn't matter what kind of collision you have. Momentum is always going to be conserved in an event like a collision. The difference is the kinetic energy. If you've ever seen a slow motion video of a basketball hitting a floor, it doesn't actually keep its shape when it hits the floor. A basketball is round. So when it hits the floor, because it's made of a rubber-like material, it actually flattens out when it hits the ground. It deforms. And then as it comes back up off the floor, it reforms. And that takes energy, kinetic energy. So the kinetic energy before it hits the floor will not be the same as it comes up off the floor, because some of that kinetic energy will have been converted to deforming the object. We call that deformation energy. Now, momentum is conserved for both, but kinetic energy is only conserved for elastic collisions. It is not conserved for inelastic collisions. So that's how we know what type of collision we have. What happens to the kinetic energy tells us. Okay, there is also a special case for the inelastic collision, and that is the perfectly inelastic collision. In this special case, the objects actually stick together. Now, in some inelastic collisions, they can also bounce off each other. But perfectly inelastic collisions, they stick together and share the total momentum as if they were one object. A good example of that would be, say, two cars colliding and their bumpers lock and they slide off together. Okay, or maybe two football players, one tackles the other and they fly off together one tackling the other. A good example of looking at conservation of momentum, look at this train. We have a 10,000 kilogram train, and it's moving along the track at 3 meters per second. We'll take the forward motion to be positive. It collides with a 5,000 kilogram boxcar. So there's the mass of our second object. The boxcar is initially at rest on the track. The train collides with the boxcar and they lock together. They couple. That's what they do to put the train, the length of the train together, is they lock the boxcars. Now, the first thing they want us to do is determine the initial momentum of the locomotive and the initial momentum of the boxcar. So, using an L for subscript for locomotive, the initial momentum of the locomotive would be the mass, 10,000 kilograms, times the speed, 3 meters per second, and obviously 3 times 10,000, that's 30,000 Newton seconds, okay? Now, the initial momentum of the boxcar would obviously be 0. If you are not moving, your speed is 0, and 0 times anything is 0. Next, they want us to determine the total initial momentum of the system, both together before they collide. Well, that's kind of obvious, but we're going to write it out. The sum of the initial momentum would be 30,000 plus 0, or 30,000 Newton seconds. The locomotive and the boxcar together have this total momentum, even though they're not yet combined. They've not made contact yet. Now, what is the total final momentum of the system just after they collide? Well, according to conservation of momentum, it has to be the same. So we can say that the sum of the final momenta of the two cars must also be 30,000 Newton seconds, because momentum absolutely must always be conserved. It doesn't matter that this is a perfectly inelastic collision. Momentum is still always conserved for any kind of collision. Now, if they are stuck together by the coupling, then what is the final speed of the system? Well, the two are now stuck together as one mass at some final velocity. So, the sum or total momentum must equal the total mass times the final velocity of the two. So now, we can solve for that final velocity, take the 15,000, divide it to the other side, and we get 2 meters per second. So the locomotive and the boxcar will continue rolling down the track at 2 meters per second. Okay. Let's look at one more example of a linear collision, but this time we're going to look at 3 objects colliding at the same time, like on a ping pong balls on a table. So you have 3 identical ping pong balls. That means they all have the same mass. They are involved in a collision as pictured. Ball A has an initial velocity to the right, since that's the direction we normally take to be positive. It catches up to and collides with ball B that is moving a little bit slower at only 0.3 meters per second to the right. At the same instant, ball C, traveling at -4 meters per second, that means to the left, also collides with ball B. The final velocity of ball A is -0.25 meters per second, and ball B comes to a complete stop. What is the final velocity of ball C? All right, now we know ball A is going to bounce back in the other direction, and ball B is going to stop. What are the possibilities for ball C? Well, ball C will either have to stop because it can't go through ball B to continue to the left, or it will have to bounce back in the other direction. And we're going to determine that by looking at the law of conservation of momentum to solve this problem. Now, because we have 3 objects with a variety of velocities, initial and final, I like to set up a little chart, okay? So right here, I set up a chart for each ping pong ball, initial velocity and final velocities. And here's our unknown for ball C. Please make sure you watch out for signs. Remember, momentum is a vector, and those signs make a big difference to the math. So now we're going to set up the law of conservation of momentum. We have the initial momentum of ball A, the initial momentum of ball B, and the initial momentum of ball C. We have the final momentum of A, the final momentum of B, and the final momentum of C. In this particular instance, because they tell us the mass of all the balls are the same, they're identical balls, all of the masses cancel out because it's in every term. We also know that the final velocity of ball B is 0, so we can drop that one. Now we're left with this, and I simply chucked in the velocities with their respective directions. We solve for the final velocity of C, and we get positive 0.65 meters per second. So this is telling us ball C didn't stop. It bounced back to the right at 0.65 meters per second. Okay? We are going to stop there for now. We will look at non-collisional events on Wednesday, I believe. So what you need to do now is to go into your Monday folder and see what activities you have to go along with this. All right, I'll talk to you guys later. Bye-bye.